Hey guys, let's continue our lecture. From last time we were talking about the structural components of our atmosphere. Recall that we have distinctive layers in our atmosphere and they're defined by marked changes in temperature, right? And those changes in temperature create different layers, and each layer has unique sort of qualities and characteristics. The innermost layer is what I want to focus on today, which is the troposphere, because this is the layer that we live in, right? So we're sort of familiar with it. It's the layer where weather occurs, right? Because it's really the only layer that contains water vapor. Um, and it is the layer where the greenhouse effect occurs. And therefore, this is the layer that is experiencing uh, global climate change, or perhaps global warming. Um, whether or not this global warming is influenced by humans or not is, I suppose, up for debate. But the fact that the Earth is warming isn't really debatable. It is. And since 1980, in fact, the temperature has increased by 1 degree Fahrenheit. There is no dispute there. The question of whether or not humans are involved with that is debatable, although amongst scientists, it's really not. I think most of that debate occurs in the popular press and in politics. Nevertheless, when we analyze this, I think it's important to understand the composition of the troposphere because ultimately it's the composition that determines the atmospheric conditions and specifically the atmospheric temperatures. So take a deep breath. Let's look at that composition because that breath consists of primarily, as you can see, nitrogen at 78%. 21% of that is oxygen, leaving 1% to other gases. And so you might be quick to dismiss that 1%, but it turns out that is critical because it's the composition of this 1% that can really throw things off, right? It can make atmospheric conditions in global climate into a barren and frozen wasteland or to one that is being cooked all over. So this 1% is going to determine the major characteristics of the troposphere. So let's look at that 1%. Mostly, that 1% consists of what we call greenhouse gases. And these greenhouse gases include water vapor, carbon dioxide, methane, and nitrous oxide. Water vapor is without a doubt the most abundant greenhouse gas, although it varies wildly, right? You know, if you're at the poles, it could be 1/100th of a percent, but in equatorial regions, it actually ramps up significantly all the way up to 4% of atmospheric composition. So it does vary wildly, but nevertheless, it is the most abundant greenhouse gas, followed by carbon dioxide, and we have methane and nitrous oxide. Now, these gases are critical. So before we start attacking them, they're naturally occurring, and without them, life on Earth really wouldn't be possible because they make life livable. They make the planet hospitable. Without these gases, the Earth would be a frozen wasteland. Right? And because the greenhouse effect basically allows the Earth to be insulated, like we're covered by a nice thermal blanket. And that's really important. And the greenhouse effect itself is probably the most widely accepted of the atmospheric theories there are in modern climatology. So this really isn't disputed, and of course this is how our troposphere functions. So how does this greenhouse effect work? Well, it works like a greenhouse, obviously, right? We know that a greenhouse has glass surrounding it, just like our atmosphere surrounds the Earth, right? And so how it actually works is that we have our sun, which is radiating all sorts of energy across empty space in the form of electromagnetic waves, right? And these waves are defined from each other, and they're distinguished from each other based on the wavelengths. For example, we can define a wavelength by the distance between the crest to the crest of another wave, right? And that's what defines the wavelength. And now we have different forms of energy based on those wavelengths, and the majority of the energy that reaches Earth's surface comes in the form of visible light. That visible light has a relatively short wavelength, meaning it's pretty intense, right? High intensity, high frequency. And since it's of such high intensity, it is capable of passing through our atmosphere, or in this case, it is capable of passing through the greenhouse glass, right? And since it's capable of passing, that means it reaches Earth's surface. In fact, over 50% of the incoming visible light, the short wavelength, reaches Earth's surface. The other percentage actually gets absorbed or refracted or reflected and sent back out into space, but a good chunk of it reaches Earth's surface. When it does, it gets absorbed. And then there's a transformation of energy. And like any other transformation of energy, in accordance with the second law of thermodynamics, it will degrade as waste heat. Or in other words, it will degrade in the form of infrared heat energy. So it gets absorbed, and then that heat energy, that infrared, then gets re-radiated from Earth's surface, where it is then sent back out into outer space. Now, because we have greenhouse gases, or in this case, because we have a greenhouse glass, some of that infrared energy is trapped, and therefore it warms the lower troposphere. And the way that works is that the greenhouse gases like water vapor, carbon dioxide, methane, they get excited by this infrared energy. And when they get excited, they re-radiate even more infrared energy that has an even longer wavelength. And ultimately what that does, it increases the average kinetic energy in the troposphere, causing the Earth to warm. And that helps to insulate and keep our Earth livable. So the issue arises as to, what happens if we start changing the chemical composition of our atmosphere? What if we start increasing the concentration of these greenhouse gases and therefore basically thicken that insulative blanket or thicken the glass of the greenhouse? Well, what happens then? Well, obviously that means more heat energy will be trapped, and therefore global temperatures will rise. And so many are concerned that we're doing this, and we're doing this through human activities. We are fundamentally changing the composition of our atmosphere. To be fair, climates have always changed, right? Over the last 900,000 years, we've gone through several glacial periods. We've gone through interglacial periods, and we are currently in one right now. But now we're concerned because the rate of change is accelerating. And of course, this is intensifying this natural greenhouse effect. And we don't know what the outcome will be. And so, what are we doing to change the atmospheric composition? Here's a list of some of those human activities. The first one is first on the list, probably because it's the most important, right? We are burning and combusting fossil fuels. Coal, for example, probably the biggest culprit here, is giving off a lot of carbon dioxide because coal, basically, we know, is a fossil fuel. So it's basically fossilized sunlight, and those prehistoric plants took in carbon dioxide and then became locked away in Earth's crust. They were really never going to see the light of day again until humans have come along and we've harvested that coal and then we burned it and combusted it for energy. And of course, when you burn anything, you do so in the presence of oxygen, so that carbon then becomes carbon dioxide and it gets released into the atmosphere, contributing to a net increase in carbon dioxide emissions in our atmosphere. 70 to 75% of our carbon dioxide emissions is a result of coal combustion. So that's big. And of course, these carbon dioxide gases remain in our atmosphere for 100 to 120 years. So they keep doing this work of trapping more and more infrared energy. And so the major concern is, well, how do we know we've been increasing these concentrations over time, and how do we know we can attribute it to human activities? Well, a lot of our research comes from studying glaciers and polar ice caps. And so we go to places like Antarctica, we go to places like Greenland, where these glaciers are several miles thick, and they read like ancient scrolls. And by drilling into them and pulling out ice cores, basically we're looking at a history of our atmosphere and how that has changed over thousands and thousands of years. Because these gases become trapped in the ice. And so by studying the concentration of those gases over time and comparing it to temperatures, we know temperatures of our atmosphere over time have changed because we can also study various isotopes that are buried in that ice as well. And so by looking at the changing atmospheric composition of carbon dioxide, for example, and looking at the changing temperatures, we notice they fit really well together. There's a strong correlation that shows as CO2 increases, so does atmospheric temperature. And so we noticed that before the Industrial Revolution, before we started burning fossil fuels, the average concentration of CO2 in the atmosphere was right around 280 parts per million. Well, up until last year, it's been increasing, and it's still increasing, in fact. And we noticed that we just reached 400 parts per million. And they suspect if we continue along this trajectory, that will eventually reach 560 parts per million by the year 2050. Many climatologists are very concerned about this value because they've determined, based on certain models, that we have a threshold value of around 450 parts per million. In other words, it's sort of a tipping point, and if we exceed 450 parts per million, there will be runaway warming that we can do nothing about, and the implications will be far-reaching. Well, how else are we increasing CO2 in our atmosphere? We're removing trees, right? We know trees and forests are critical carbon sinks. They take in carbon dioxide from our atmosphere. So when we cut them down and burn them, not only are we releasing the carbon in their biomass, but we're removing an area of the world that would ultimately remove carbon from the atmosphere. Therefore, it will contribute to a net increase of CO2. Urbanization leads to warming temperatures as well. We're removing trees again. We're replacing them with concrete and dark asphalt. And what this is doing, it's allowing for greater absorption of insulation at Earth's surface. It's disrupting wind patterns. And oftentimes, city environments have microclimates or are considered urban heat islands that are several temperatures warmer than the surrounding countryside. Moreover, additional greenhouse gases like methane, which has an average residence time of about 12 to 18 years in our atmosphere, but has a relative warming potential compared to carbon dioxide of about 23 to 25 times greater the potency of CO2. Well, how are we increasing methane emissions? Since the Industrial Revolution, 70% of our methane emissions over the last 275 years have come from human activities. And these human activities come from raising cattle, right? Cattle belch. They're farting constantly, and in doing so, they release methane, a very potent greenhouse gas. So livestock, rice paddies, right? These are submerged vegetation where there's going to be anaerobic decomposition, which can also release methane. The permafrost, as it melts, it releases methane hydrates, which will also contribute to increased warming. Landfills, again, anaerobic decomposition. Sewage treatment plants, natural gas deposits, and as we transfer natural gas for energy use, oftentimes those pipelines leak, also releasing more methane. So lots of different sources coming from methane. Nitrous oxide is another very, very potent greenhouse gas that is about 300 times more potent than carbon dioxide. It's released from burning fossil fuels, automobile emissions, for example, as well as from inorganic fertilizers. So this nitrogen that we put in our fields releases nitrous oxide, which is also a very potent greenhouse gas. And these emissions have increased by 20% over the last 275 years. Finally, the only sort of anthropogenic, purely anthropogenic or human-derived greenhouse gas are CFCs. And not only do these contribute to ozone depletion, but in our troposphere, they have amazing warming potential. 900 to close to 8,500 times the warming potential than carbon dioxide. And so as we release these, they also contribute to human-induced climate change. So that is it for today on global warming. We will continue to look at this and we'll start exploring what the implications are for the future of our climate. Thanks, guys.